Hello everyone and welcome back to Nunley Math. I'm Aaron Nunley. Thank you so much for joining me here today as we begin a new unit on exponents and scientific notation. Exponents and scientific notation. Now this unit is probably going to be about, I'd say 7 or 8 videos. We're going to talk about some basic ideas of exponents, how exponents affect integers or positive and negative whole numbers. I'm going to talk about how exponents can be affected by fractions. We're going to talk about how we can represent some very, very large numbers or very, very small numbers using exponents. We're going to look for some patterns that happen to emerge. So let's go ahead and get started. We've got a little bit of ground to cover today, so we're going to go ahead and get moving. An exponent is a raised number or variable in mathematics that indicates the degree or power to which an expression called the base is raised. It indicates how many of that base are being multiplied together. Now that's some pretty fancy math talk, but let's break this down for you. If I have 2 to the third power, in this case the 2 is known as my base, the 3 is known as my exponent. Now, what does that mean? Well, the 3 tells me how many of the base are being multiplied together. So 2 to the third in exponent form could be written out in expanded form as 2 times 2 times 2. And of course, hopefully we know that 2 times 2 is 4 and 4 times 2 is 8, which is the standard form in which we typically would write a number. Notice, exponent form has a base to an exponent. The exponent tells you how many of that number are multiplied together to create a number in standard form. Now, ideally, we want to be able to get from this 2 to the third power or exponent form all the way over to the 8, which is our standard form, without having to go through expanded form every single time. But I find that especially early on as you're studying exponents, seeing the expanded form is very helpful for picking out patterns, as well as keeping us from getting confused as to what is occurring with the exponent. So what I've got here is I've got a list of 6 powers of the base 2. Notice you have 2 to the first power. We refer to this as a first degree, or in expanded form, it's just a 2 by itself, which in standard form is also a 2. A second degree term would have an exponent with a 2. This says 2 to the second, or 2 times itself, which is, of course, 4. 2 to the third is a third degree exponent. It says take 3 2's and multiply them together, which, of course, is 8. 2 to the fourth says take 4 of them, 16. 2 to the fifth says take 5 of them, which is a 32. And 2 to the sixth says take 6 of them, which is 64. Now, I can tell you that it is very, very common for math teachers to use these particular exponents a lot. The base of 2 with the exponents 1, 2, 3, 4, 5, and 6. The reason for that is sometimes when we deal with exponents, our numbers grow very quickly, and we'll actually talk about that in a future lesson. But it often forces us to work with small numbers. So since 2 is a pretty small prime number, we can multiply it together without getting too huge numbers too quickly over here on the right. Because of that, it's to your advantage to recognize 2, 4, 8, 16, 32, and 64 as being powers of 2 on site. So whenever I see the number 32, I instantly recognize that as being a 2 to a power of something. I put it in here so that you have those in a list. If you don't have a set of notes to go along with this, I would recommend screenshotting this or using your snipping tool to take a picture of that, because having that handy is certainly going to save you a lot of time when you're working through problems that are a little longer. Now this table just gives us an opportunity to practice applying exponents to bases that are different from just a 2. For example, this is 10 as my base, and it says to the 5th power. If you feel pretty comfortable and confident in your ability to work with exponents, I'd recommend pausing the video and doing these on your own. And then once you've finished that, just skimming through the video quickly to see if my answers match yours. What I'm going to do is just work through these for students who might be having some difficulty. 10 to the 5th in expanded form is just 5 10s multiplied together. 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000, times 10 is 100,000. Remember before when I talked about the need for mathematicians to use small bases? This is an example of what happens when you get a larger base. You end up getting very large numbers, and sometimes that's difficult for students to work with. How about 5 to the third? That just says take 3 5s and multiply them together. 5 times 5 is 25, times 5 is 125. 4 to the fourth says take 4 4s, multiply them together. 4 times 4 is 16, times 4 is 64, times 4 is 256. Notice here I have -3 to the 6th power. That's 6 negative 3s. 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243, times 3 is 729. 2/3 to the 5th is just 2/3, 2/3, 2/3, 2/3, 2/3. Using our multiplication of fractions rules, we know we just multiply the numerators, 2, 4, 8, 16, 32. And we multiply our denominators. 3 times 3 is 9, 27, 81, 243. Again, notice the 2's and the 3's are popping up quite often. As I mentioned in the other slide, we want to be careful about getting numbers that are too large. So you're going to see multiples of 2 and 3 occur quite frequently. Hence the reason we had that list of 2's on the earlier slide. It might be worth your time to memorize the first few multiples of 3 as well, the first several powers of 3. 1/8 to the 3rd power is just 3 1/8. 1 times 1 times 1 is easy, that's 1. 8 times 8 is 64. 64 times 8 is 1/512. Not too bad, right? Tell you what. One of the things that you might be asked to do by your teacher when you're studying exponents is to take something that's written in expanded form and change it into exponent form. That's actually not real hard because remember, all the exponent does is says how many of this number are multiplied together. So if I have 2 times 2 times 2 times 3 times 3 times 3 times 3 times 3, all I'm going to do is I'm going to look over here and I'm going to say, how many 2's are multiplied together? Well, I see 3 of them. If I could draw a 3, there we go. How many 3's are multiplied together? Well, there are 5 of them. This is 2 to the 3rd times 3 to the 5th. I'm taking 3 2's times 5 3's. Not bad, right? You want to try that one on your own? Notice it doesn't matter what order these are written in. The commutative and associative property allows me to rearrange and regroup these all I want. What's important is how many there are. There are 5 R's and there are 2 S's. R to the 5th, S squared. If you feel pretty confident, you might want to pause the video, try this one on your own. I'm going to keep going for those that might be wanting to watch. I have 1/2. I have another 1/2. There are 2 of those. I have an X, an X, and an X. There are 3 of those. And I have a Y and a Y. That's 2 of those. I have 2 1/2s. That's 1/2 squared. X to the 3rd, Y to the 2nd. Again, this shouldn't be too awfully bad for you. I don't think. If you are having trouble, you certainly can go back and watch this again. But I think most of that should make pretty good sense once you've seen it in expanded form. Now, as I mentioned, there are some exponents that are used more frequently than others, some bases that are used more frequently than others. That's why I suggested that you take that chart that had the 2's in it and you try and commit those to memory. Additionally, what I would recommend is that you take the time and memorize the perfect squares and the perfect cubes from 0 to 24 for the squares, and from 0 to 10 for the cubes. Now, in our earlier unit where we talked about order of operations, and we talked about squares and square roots, you probably have already seen many of these. I'm going to recommend that you commit at least this many to memory. Again, they are going to be, it is a little bit of work to find these, but they are going to be coming up very, very frequently in later mathematics. And if you have them memorized, you just save yourself a lot of time and effort in trying to calculate those out. Now, if we were actually in class, I would have you try and fill those out on your own. But since we're not in class and this is a YouTube video, I'm going to assume that if you want to figure those out on your own, you can pause the video and do that. I'm just going to go ahead and show you what they are. Notice I added 25 squared in here as well. The 25 squared I would require my students to memorize. In fact, in my class, I always give a quiz where I have the students take a blank sheet of paper and list all the perfect squares from 0 up through 25. And that quiz will actually be coming up here in a week or so for us. So just know that memorizing these is certainly advantageous to you. By the way, we do call them perfect squares because each of these represents the area of a square with sides of these lengths. Notice 2 times 2 gives us 4. That's why they're called perfect squares. There's certainly a geometry connection there. Perfect cubes just mean this number times itself again. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. These happen very, very frequently. These are the volumes of a cube. Remember, the volume is found by length times width times height. So each of these would represent the volume of a cube that is made from whole numbers. Again, this is something that I would probably screenshot or copy down or make a picture of. Even if I didn't memorize it, I would put those in a list and keep them handy so that if I was working on some homework, I wouldn't have to look them up every time because they do happen quite frequently. Now, a second thing you might be asked to by your teachers, you might be asked to use greater than, less than, or equal to compare exponent expressions. Your best bet for doing that is just to put those into simplest form. 3 squared is 3 times 3, which is 9. 2 to the third is 2 times 2 times 2, which is 8. 9's bigger than 8. It's as simple as that. If you feel pretty comfortable, I would recommend that you pause the video and try these next few on your own. Otherwise, I'm going to keep right on going. 2 to the 6th is 64, sorry. 6 squared is 6 times 6, which is 36. 64 is greater than 36. Down here, 5 to the third. 5 times 5 times 5 is 125. 3 to the 5th is 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243. This is less than. Over here, 2 to the 5th, well, 2 to the 6th was 64, so that tells me 2 to the 5th is 32. Negative 2 to the 5th is just a little bit tricky for people. Please keep in mind that this is not only 5 2's, but it's also 5 negative signs. So this would look like this. Negative 2 times negative 2 is 4, times negative 2 is negative 8, times negative 2 is 16, times negative 2 is negative 32. This is greater than. There's some really interesting things that happen when we talk about exponents on negative bases, but we'll get to that in just a little bit. I don't want to get too far ahead of ourselves. How about this? You might be asked to evaluate or find the value of an expression. For example, what would g to the 5th times h be if g is a 2 and h is a 7? Well, in my class, if you were doing this on a separate sheet of paper, I would have you rewrite this, plug in the 2 for g, plug in the 7 for the h, that's here, and then use order of operations to simplify. Remember, order of operations says exponents first, multiplication afterwards. Here's a second one. Again, I would recommend pausing this, trying it on your own, and then checking to see if you've done it the same way I have. I would have my students rewrite, plug in a 1 for the x and a 3 for the y, do the exponents, and simplify. How about this? Sometimes you might be given several exponent expressions. You might be asked whether or not they have the same value. Here's an example of that. If I have 4 squared, negative 4 squared, negative 4 squared, and negative 4 squared, there's my cursor, and I ask you, are these all the same value? Your best bet is to look at them and put them into standard form. 4 squared is 4 times 4, which is 16. Negative 4 squared is negative 4 times negative 4, which is also 16. Now notice here, the 2 is on this set of parentheses. That means I have 2 of everything that's inside of here. Well, that's a negative sign and 2 4s, or a negative 16. Take a moment and compare this with this. Notice when the negative sign's on the inside, I have 2 negative signs as well. When it's on the outside, I only have 1. A lot of students get really freaked out by this example. They're trying to figure out, is this like this or like this? I'd recommend that if you need a second to pause the video and think about that, you go ahead and do that. Otherwise, I'm just going to keep right on going. This actually says the same as this example. I have 1 negative sign and 2 4s, giving me a negative 16. I would put a little star next to that if I was taking notes on it, because this is the one everybody tends to mess up. They like to think that this is a negative 4 squared, but it's not. Only the 4 is squared because only the 4 is connected to the exponent. The only time that I would have 2 of the negative signs would be if it was in parentheses. Again, this is the one that's going to cause people the most trouble. Put a little note there. There is a lot of discussion that goes into this and why this happens. It's not appropriate for us to look at those right this minute, but it's certainly something that I would like to go back and revisit in a future video. The 4 squared happens first, then you make it negative. How about this? Can you see a pattern here, and then can you generate a rule? I would recommend pausing the video, writing these out in expanded form, and then in simplest form as you're looking for the pattern. Negative 3 to the first says negative 3, which is just negative 3. Negative 3 squared is negative 3 times negative 3, which is positive 9. 3 negative 3s makes negative 27. 4 negative 3s is 81. 5 negative 3s is negative 243. And 6 negative 3s is 729. Now, I might have gone a little overboard with color coding those, but hopefully you can spot pretty easily that all the ones that are in purple are negative, and all the ones that are in red are positive. In fact, that's due to the fact that these are odd exponents. Odd exponents will always give you an odd solution. Even exponents will always give you an even solution. The reason for that is because a negative times a negative equals a positive. If I have an even number of negatives, this positive gets multiplied by a negative and becomes negative. Then that negative gets multiplied by a negative and becomes a positive. If I have 5, every pair is going to give me a positive. This leftover is going to make it negative. Notice positive, positive, positive. All the evens will end up being a positive solution. All the odd exponents will give you a negative solution. It's a nice little tidbit that comes in handy every once in a while. If I were to give you an expression or an equation like this, x to the third equals 27, can you think of a number that times itself and times itself again would equal 27? If you need some time, absolutely pause the video. I'm going to keep going ahead. The solution there is 3. Because 3 times 3 times 3 is 27. These are a little tricky, right? How about this one? Something that times itself equals 81. Most people think they do pretty well with this because most of us get the number 9. Because 9 times itself is 81. But this one actually has a second answer. Can you spot it? It's actually a negative 9. Because negative 9 times itself also equals an 81. Notice negative 3 did not work over here because negative 3 times negative 3 times negative 3 would be an odd number of negative signs, which would give you a negative 27. Whenever you've got an even exponent, you've got to be careful to make sure you get both of the possible solutions. Here's one that's even harder. How many 4s have to be multiplied together to give you 256? You might want to pause. It takes 4. 4 times 4 is 16, times 4 is 64, times 4 is 256. A little typo there. Thank you. Last one. How many 3's have to be multiplied together to get a 243? Again, I'd recommend pausing the video to try this. It's actually 5. 3 times 3 is 9. Times 3 is 27. Times 3 is 81. Times 3 is 243. Notice again, the base of 3 and perfect squares and perfect cubes happen a lot because I got to be careful not to make my numbers too large. This is the last thing we got to do. We're going to evaluate some expressions that involve exponents. We've done a little bit of this before, but I just want to give you a little more experience with it and throw in a few that are more challenging. Remember when we do our evaluating expressions, we always follow our order of operations. Anything that's inside parentheses or a grouping symbol gets done first, followed by exponents, which is what we're talking about here today, and then multiplying and dividing, we do an order from left to right, and adding and subtracting, we do an order from left to right. So in this problem, I'm going to do the exponents first. 3 squared is 9. 4 to the third is 64. You get 73. Notice, technically, I should have done this, then done this, possibly in 2 separate steps. But because I knew they wouldn't affect each other until they got added at the end, it was okay to do them at the same time. Again, I'm going to start to do these a little quicker, assuming that you're pausing the video in between to try them on your own. 5 to the third is 125. 2 squared is 4. You get 129. How about this? This is 32 minus 25, which is 7. How about this one? There are no parentheses, so when I do my exponents, I get 49 plus 8 times 9. What's the next step you're supposed to do? That would be the multiplication. Be careful not to get in too big of a hurry here, and you're going to add last. 2 to the fourth is 16. 6 squared is 36. That is the same as adding negative 36, which is a negative 20. How about this one? I want you to think about this for just a second. I'm going to do it slightly different than I did this one. Notice the equation is the same, but instead of doing my exponents first, I want to think about what this minus sign means. Remember in our integers unit, we talked about the fact that subtraction is the same as adding the opposite, right? The definition of subtraction says that this equation right here, which we already know is negative 20, has to give me the same solution as this, meaning it has to be a 16 plus a negative 36 to get a negative 20. Notice what happened here. Negative 6 squared gave us a negative 36. Remember that other slide where we were talking about that negative exponent, or that negative base with an exponent, and how the 2 only applies to the number, not the sign? This is an example of why that's important for us. Because if negative 6 squared meant this 2 applied to both, I would have got a positive 36 and a, is that 52? Here. In order to maintain consistency between my rules in math, it's important that we validate the definition of subtraction while at the same time making sure that our exponent rules don't mess that up. This is a good reason why we like to have that exponent only apply to the number. If I wanted it to apply to both, I'd use the parentheses, but I need to make sure this is consistent. Last one. Hopefully you realize this is 25 plus negative 8, or 25 minus 8, which is 17. I know that's a lot of information all at once. Hopefully a lot of it was review and cleaning up some odds and ends that might have been unfamiliar to you. I like to begin my unit with this type of a lesson because some of the things we're going to do over the next couple of videos can be a little tricky, and it's important to make sure we have a really solid foundation before we get into those. As always, thank you so much for being with us. Make sure you take the time to leave us a comment in the comment section, especially if there's something you noticed that we could do a little bit better, or if there's something you found extremely helpful. Make sure you smash that like button. Make sure you turn on your notifications by ringing that bell so that you can follow along with all our new lessons here at Nunley Math. Thank you so much. You guys take care of yourselves. Appreciate you being with us. Bye-bye.